Welcome to this comprehensive lesson on the constant rule in differentiation. Today, we're going to explore one of the most fundamental concepts in calculus that will serve as the foundation for everything else you'll learn. The constant rule states that if you have a function f of x equals c, where c is any constant number, then the derivative of that function, written as f prime of x, is always 0. But what does this actually mean? Let me show you with some concrete examples of constant functions. Here are three examples. If f of x equals 5, then f prime of x equals 0. If g of x equals -3, then g prime of x equals 0. If h of x equals pi, then h prime of x equals 0. Notice the pattern. No matter what the constant value is, the derivative is always 0. Now let's understand why this makes sense by looking at what constant functions look like graphically. Here we have a graph showing the function f of x equals 2. Notice that this creates a perfectly horizontal line. No matter what x value we choose, the y value is always 2. Since this line is perfectly horizontal, its slope is 0 everywhere. And remember, the derivative of a function tells us the slope of the line at any point. Since the slope is 0, the derivative must also be 0. This makes perfect intuitive sense. Constants don't change, they stay the same no matter what. And derivatives measure the rate of change. So if constants never change, then their rate of change is 0, which means their derivative is 0. This is why the constant rule is so fundamental. It captures this basic mathematical truth. This rule will be the building block for all the more complex differentiation techniques we'll learn. Understanding why the derivative of a constant is 0 will help you master calculus step by step. To truly understand the constant rule in differentiation, we first need to grasp what a derivative actually represents. A derivative is fundamentally about measuring change, specifically the instantaneous rate of change of a function. Think about a car driving down a road. The rate of change tells us how fast the car's position is changing with respect to time. In other words, its speed or velocity. In mathematics, we express this concept using function notation. If we have a function f of x, then f prime of x, written as fx, represents the derivative, the instantaneous rate of change of the function at any point x. Graphically, the derivative has a very clear interpretation. It represents the slope of the tangent line to the function's curve at any given point. For example, consider a curved function like y equals x squared. At different points along this curve, the slope of the tangent line changes, which means the derivative changes. Now, what happens when we have a constant function? A constant function, such as f of x equals 5, creates a horizontal line on the graph. Since this is a horizontal line, it has no rise over run. The line doesn't go up or down as we move from left to right. It stays perfectly flat. When we draw a tangent line to any point on this horizontal line, the tangent line is identical to the original line. It's also horizontal. Since a horizontal line has 0 slope, the derivative of a constant function is always 0. This makes perfect sense. A constant value doesn't change, so its rate of change is 0. This fundamental understanding that derivatives measure rates of change and constant functions have 0 rate of change is the foundation of the constant rule in differentiation. Now that we understand what the constant rule means, we need to learn how mathematicians write it down. There are 3 main notations used to express the constant rule, and each one has its own purpose and context. Before we dive into the notations, you might wonder why we need 3 different ways to write the same thing. The answer is that mathematics has evolved over centuries, with different mathematicians developing their own systems. Each notation also emphasizes different aspects of the derivative, and different fields of study tend to prefer different notations. The first notation is called Leibniz notation, named after the German mathematician Gottfried Leibniz. In this notation, we write the constant rule as d over dx of c equals 0. Let me break down what each part means. The d represents a differential, dx means with respect to x, and c represents any constant. Together, this reads as the derivative of c with respect to x equals 0. This notation is most commonly found in calculus textbooks and formal mathematical writing. It clearly shows what we're differentiating and with respect to which variable. The second notation is called prime notation, also known as Lagrange notation after Joseph Louis Lagrange. In this system, we first define our function f of x equals c, where c is a constant. Then we write the derivative as f prime of x equals 0. The prime symbol, this little apostrophe, indicates that we're taking the derivative of the function f. This notation is particularly popular in physics and engineering because it's compact and easy to write quickly. When you see f prime, you immediately know it's the derivative of f. The third notation is operator notation. Here we use the symbol d to represent the differential operator, and we write d of c equals 0. Sometimes you'll see it written with a subscript x, like this, to specify which variable we're differentiating with respect to. The d represents a differential operator, and the square brackets show what we're operating on. This notation treats differentiation as an operation that we perform on functions. It's most commonly used in advanced mathematics and when studying differential equations. Now here's the important point. All three notations are completely equivalent. They're just different ways of writing the same mathematical truth. Whether you see it written in Leibniz notation, prime notation, or operator notation, they all express the same fundamental truth. The derivative of any constant is 0. The notation you encounter will depend on your textbook, your professor, and the field you're studying. As a student, here's my practical advice. First, learn to recognize all three notations so you won't be confused when you encounter them in different contexts. Practice converting between the notations to deepen your understanding. Always use the notation that your textbook or professor prefers to stay consistent. And most importantly, remember that regardless of how it's written, they all mean exactly the same thing. The derivative of a constant is 0. Now we'll work through 3 examples to see the constant rule in action. Our first example is the simplest case, a positive integer constant. Consider the function f of x equals 7. Here, 7 is our constant. It never changes no matter what value x takes. To find the derivative, we apply the constant rule. Since 7 is a constant, its derivative with respect to x is 0. Therefore, f prime of x equals 0. The derivative of any constant is always 0 because constants don't change. Now for our second example, we'll look at a negative irrational constant to show that the rule works for all types of constants. Example 2 involves the function g of x equals negative pi. Here we have both a negative sign and the irrational number pi. Even though negative pi is irrational and negative, it's still a constant. The constant rule tells us that the derivative of negative pi is 0. So g prime of x equals 0. And notice that it doesn't matter whether the constant is positive, negative, rational, or irrational. The derivative is always 0. For our final example, we'll examine a constant involving a square root to demonstrate that the rule applies to all constant expressions. Example 3 features the function h of x equals the square root of 2. This is another irrational constant, but expressed as a radical. The square root of 2 is approximately 1.414. But regardless of its exact decimal value, it's still a constant. Applying the constant rule gives us 0. Therefore, h prime of x equals 0. Once again, we see that the constant rule applies universally to all constants, no matter how they're written. These 3 examples demonstrate the universal nature of the constant rule. Whether we have a simple integer, a negative irrational number, or a radical expression, the derivative is always 0. The constant rule states that the derivative of any constant is 0. This applies to all constants: positive, negative, rational, irrational, integers, fractions, and radical expressions. Remember this fundamental principle as we move forward. Constants never change, so their rate of change is always 0. The constant rule isn't just an abstract mathematical concept. It appears everywhere in the real world, from physics to economics to engineering. When we understand that the derivative of any constant is 0, we can recognize this pattern in many practical situations. Our first example comes from physics. Imagine a car traveling on a highway at a perfectly constant speed of 60 miles per hour. Since velocity is constant, we can write this as a function, v of t equals 60. This is a constant function, where velocity doesn't change with time. Now, acceleration is defined as the derivative of velocity with respect to time. Using our constant rule, the derivative of 60 is 0. This makes perfect physical sense. If the car is traveling at constant speed, it's not speeding up or slowing down, so its acceleration is zero. Our second example comes from economics. Every business has fixed costs, expenses that don't change regardless of how much they produce or sell. Let's focus on rent. The monthly rent is $7,000, and this amount stays the same every month. We can write this as a function, C of t equals 7,000. The rate of change of fixed costs is their derivative. Since 7,000 is a constant, its derivative is zero. This means fixed costs have no rate of change. This zero rate of change tells us that fixed costs remain stable over time, which is exactly what we expect from expenses like rent and insurance. Our final example comes from engineering. Consider a thermostat maintaining a room at exactly 72 degrees Fahrenheit. In steady-state conditions, the temperature remains constant over time. We can express this as T of t equals 72. The rate of temperature change is the derivative of temperature with respect to time. Since 72 is constant, this derivative equals zero. This zero rate of change confirms that the system is in perfect steady state. The temperature is neither increasing nor decreasing, which is exactly what good temperature control should achieve. These three examples demonstrate the power and universality of the constant rule. Whether we're analyzing motion in physics, costs in economics, or control systems in engineering, the same mathematical principle applies. Understanding these real-world connections helps us see that calculus isn't just abstract mathematics. It's a powerful tool for describing and analyzing the world around us. The constant rule, simple as it may seem, is fundamental to understanding rates of change in countless practical situations. The constant rule doesn't exist in isolation. It serves as a fundamental building block for many other differentiation rules. Understanding how the constant rule integrates with other rules is crucial for mastering calculus. Think of the constant rule as the foundation stone. Three major differentiation rules are built directly upon this foundation: the constant multiple rule, the sum and difference rule, and even the chain rule. Our first example demonstrates the constant multiple rule. We need to find the derivative of 5 times x squared. The constant multiple rule states that the derivative of a constant times a function equals the constant times the derivative of the function. First, we identify the constant 5. According to the constant multiple rule, we can factor out this constant and multiply it by the derivative of x squared. The derivative of x squared is 2x using the power rule, so we have 5 times 2x. Simplifying, we get 10x as our final answer. Notice how the constant 5 remained unchanged throughout the differentiation process. Our second example involves the sum rule combined with the constant rule. We need to differentiate x cubed plus 7. The sum rule tells us to differentiate each term separately and add the results. We apply the sum rule by differentiating each term separately. The first term is x cubed, and the second term is the constant 7. The derivative of x cubed is 3x squared. Here's where the constant rule comes in. The derivative of the constant 7 is 0. Adding 3x squared plus 0 gives us simply 3x squared. The constant term completely disappears because its derivative is 0. Our final example demonstrates how the constant rule works within the chain rule. We need to find the derivative of sine of 3x plus pi. This is a composite function where constants appear in the inner function. First, we identify the outer function as sine of u and the inner function as u equals 3x plus pi. Notice that pi is a constant in our inner function. Using the chain rule, the derivative of the outer function sine gives us cosine, and we multiply by the derivative of the inner function 3x plus pi. When we differentiate the inner function 3x plus pi, we get 3 from the 3x term and 0 from the constant pi. The constant rule tells us that the derivative of pi is 0. Simplifying, we get 3 cosine of 3x plus pi. Notice how the constant pi remains in the final answer, but its derivative contributed 0 to our calculation. The constant rule is truly foundational in calculus. Whether constants are being factored out, disappearing entirely, or remaining unchanged while contributing 0 to derivatives, understanding this rule is essential for mastering all differentiation techniques. Now that we understand the constant rule, it's important to recognize common mistakes students make when applying it. Understanding these pitfalls will help you use the constant rule correctly every time. The first common mistake is confusing constants with variables. Remember, the constant rule only applies to terms that truly do not change with respect to the variable you're differentiating. Here's a common error. Some students think that since x is just a letter, its derivative is 0. But x is a variable, not a constant. The derivative of x with respect to x is 1, not 0. The key insight is that x changes as the input changes. Since x varies with the input, it's a variable, not a constant. Only apply the constant rule to numbers that never change. The second mistake involves coefficient constants. Students sometimes incorrectly apply the constant rule to the entire term when there's a coefficient multiplied by a variable. Consider the function f of x equals 3x. What is its derivative? The wrong thinking is, since 3 is a constant, the derivative must be 0. But this misses the crucial point that 3x contains the variable x. The correct answer is 3 because we use the constant multiple rule here. The key insight is that the constant rule applies to entire expressions that are constant, not just to coefficient numbers within variable terms. Since 3x changes when x changes, the whole expression is not constant. The third common mistake is failing to recognize disguised constants. Mathematical constants like pi, e, and square roots of numbers are still constants, even though they're written with special symbols. Here are examples of disguised constants. Pi equals approximately 3.14159, e equals approximately 2.71828, and square root of 2 equals approximately 1.41421. These are all specific numbers, so they're constants. Since these are all constants, their derivatives are all 0. The derivative of pi is 0, the derivative of e is 0, and the derivative of square root of 2 is 0. Here are 4 key tips to avoid these mistakes. First, always ask yourself, does this expression change when x changes? Second, look carefully for any variables like x, y, or t within the expression. Third, remember that mathematical constants like pi, e, and square root of 2 are specific numbers, not variables. Fourth, always double-check whether the entire expression is constant, not just parts of it. Remember this key principle. The constant rule applies only to expressions that do not contain the variable of differentiation. Master this concept and you'll avoid the most common mistakes with the constant rule. We've reached the end of our comprehensive exploration of the constant rule in differentiation. This fundamental rule is one of the building blocks of calculus that every student must master. Remember, the constant rule states that the derivative of any constant is 0. This makes perfect sense when we think about it geometrically. A constant function appears as a horizontal line, and horizontal lines have 0 slope. Throughout this tutorial, we've covered several important aspects of the constant rule. We explored its mathematical definition and various notations used in calculus. We worked through multiple examples, from simple constants like 5 and negative pi to more complex expressions involving square roots and transcendental numbers. We also discovered real-world applications where the constant rule appears, such as in physics when acceleration is 0 during constant velocity, and in economics with fixed costs. Additionally, we learned how the constant rule integrates with other differentiation rules, like the sum rule and constant multiple rule, forming the foundation for more advanced calculus techniques. Most importantly, we discussed common mistakes students make and how to avoid them. Remember to always identify what is truly constant versus what might be a variable in disguise. By understanding why the derivative of a constant is 0, rather than just memorizing the rule, you've built a solid conceptual foundation that will serve you well throughout your calculus journey. Thank you for joining me in this detailed exploration of the constant rule. If this tutorial helped you understand this fundamental concept, please give it a thumbs up and subscribe for more calculus tutorials. Leave a comment below if you have questions or suggestions for future topics. Keep practicing, and remember, every expert was once a beginner. Good luck with your calculus studies.